Welcome to this online course on machine learning for optimization. I am delighted to have you here as we explore how data science and decision-making come together. This program is brought to you by the Institute of Computer Science at Forth and the Signal Processing Laboratory, in collaboration with TwinODIS. Our goal is to move beyond simple data analysis. We want to show you how to use advanced algorithms to find the best possible solutions for complex problems. Whether you are managing an electrical grid or a factory, the principles we discuss here will help you make smarter, data-driven choices. Let us begin this journey by looking at the specific topics we will cover in our curriculum. Our course is divided into three main pillars to give you a complete understanding of the field. First, we look at supply and demand. Here we use machine learning to predict what customers want before we even start the optimization process. Second, we dive into feature selection and clustering. This step is vital because it helps us identify which pieces of data are truly important for our models. By grouping similar data points, we can create more accurate and efficient optimization strategies. Finally, we move to the hands-on section. This is where you will apply everything you have learned to real-world scenarios, using professional tools to solve actual business challenges. To make these concepts real, imagine you're running a factory that produces two main items, Product A and Product B. Product A is represented here as a navigation tablet, and Product B is a smart, wearable device. Running a factory is a constant balancing act because you deal with limited resources. You do not have infinite time, staff, or raw materials. Every time you decide to build one more tablet, you are using resources that could have gone toward a smartwatch. Your challenge as a manager is to decide the exact production mix that yields the highest benefit without running out of supplies. Let's look at the specific rules our factory must follow. First, we consider profit. Each unit of Product A earns 40 euros, while each unit of Product B earns 30 euros. Next, we look at labor. Product A is more difficult to make, requiring 2 hours of work, while Product B only needs 1 hour. We are limited to a total of 100 labor hours. Finally, we have our materials. Product A uses 3 units of material, and Product B uses 4 units. We only have 240 units of material available in total. Our objective is to calculate exactly how many units of A and B we should produce to maximize our total profit. To solve this production puzzle, we need a mathematical solver. While there are many options available, they do not all perform the same. This table shows a comparison of different solvers on a standard set of benchmark problems. You can see that some solvers, like Gurobi and spl-forth, are able to solve all 87 test cases, while others struggle with complex models. Speed is also a major factor. When we look at the runtime in seconds, Gurobi's Python interface is significantly faster than other libraries like Pulp or Pyomo, because time is money in the business world. We choose Gurobi for its superior speed and reliability. Let us take a closer look at Gurobi. It is a state-of-the-art tool designed specifically for mathematical optimization. Gurobi is used by major industries and universities all around the world because it is both fast and scalable. It can handle 3 main types of mathematical challenges shown here. First is linear programming, which we're using for our factory model. Second is mixed integer programming, which is essential when your decisions involve whole numbers, such as deciding how many full vehicles to send on a route. Finally, it handles complex quadratic and nonlinear variants used in advanced engineering. Most importantly for us, Gurobi is very friendly to use with the Python programming language. This allows us to integrate powerful optimization directly into our modern data science workflows without needing to switch between different software tools. This is the most efficient use of our 100 labor hours and our material supplies. It proves that optimization can find the perfect balance that a human manager might miss by just guessing. The engine processes the math and delivers a clear result on the right, the optimal production plan for our specific case. The math shows we should produce 32 units of Product A and 36 units of Product B by following this exact plan. We reach a maximum profit of 2,360 euros. Now we apply this optimization power to our factory scenario. On the left, we see our inputs, the factory constraints, and the variables we are testing. We feed these into the Gorobi optimization engine. We ask the solver to maximize our profit equation, which represents the total money earned from both products. Let us look at how we actually write this out in a Python script. We begin by importing the Gorobi library and creating a new model object, which we call product mix. We then define our data, such as the €40 profit for product A and the €30 profit for product B. The script then adds the decision variables and the two main rules of our factory, the labor limit and the material limit. Once we tell the model to optimize, Gorobi performs the calculations. In the red box at the bottom right, you can see the final output. The solver found the answer in a fraction of a second, default text. Product A and 36 units for product B, resulting in that maximum profit of $2,360. This script provides a repeatable template you can use for any similar business problem. While our production plan is mathematically sound, it lacks one critical ingredient: the customer. To be truly successful, we must balance our supply with the actual demand from the market. If we produce 32 tablets but the market only wants 10, we have wasted our resources. The goal illustrated here is to find the perfect overlap between what we can make and what people want to buy. We must avoid the twin traps of overproduction and underproduction. Overproduction leads to unsold inventory sitting in a warehouse, while underproduction means losing out on sales and disappointing our customers. By using machine learning to predict demand before we run our optimization, we ensure that our supply is always perfectly tuned to the real world. To predict demand accurately, we must understand the factors or features that influence our customers. We have identified 5 main factors for our products. First is the season. For example, do people buy more navigation tablets during the summer travel months? Product promotions. We track whether a buy one get one free deal or a discount is currently active. Third is the day of the week, as shopping habits often change between a Tuesday and a Saturday. Fourth is ad spend, which is the amount of money we invest in marketing to reach new people. Finally, we must watch competitor activity, because if a rival lowers their price, our demand might drop. By collecting data on these 5 areas, we can teach a machine learning model to recognize the patterns that drive our sales. To build our predictive model, we first need to look at our historical data. On this slide, we see a simulated dataset consisting of 20 random samples. These visualizations help us see how our different factors change over time. This history is the foundation that our machine learning model will use to learn how to predict the future. The top 2 charts show us the season and promotion cycles, represented by simple shifts between 0 and 1. Below those, the green line tracks the day of the week, while the red and purple lines show the more frequent changes in our ad spend and the activity of our competitors. The most important part of this data is found at the bottom. Here we see the actual recorded demand for product A and product B. By looking at all these charts together, we can start to see patterns. For example, we might notice that demand often peaks when a promotion is active or when our advertising spend is at its highest. Now let us look at the logic behind this data using the Python programming language. We use popular libraries called Pandas and NumPy to create our simulated history. In the top box, we generate 20 samples for our features, such as the day of the week and advertising spend. In the middle sections, we define how demand is actually calculated for each product. Notice that the 2 products react differently to the market. Product A is designed to have a stronger marketing sensitivity, meaning it responds very well to advertising. Product B, however, is more sensitive to competitor pressure, meaning it loses more sales when rivals are active. We also include a small amount of noise to represent the unpredictability of the real world. Finally, at the bottom, we ensure that our demand numbers never fall below 0. This code allows us to create a realistic environment to test our optimization strategies. Now that we have created our historical data set, we cannot simply use all of it for training. If we show the model every single piece of data we have, it might just memorize the past instead of learning how to predict the future. This is a common problem in machine learning known as overfitting. To avoid this, we split our data into two distinct groups, a training set and a testing set. Imagine the training set is like a textbook the model uses to study the relationships between our features, like ad spend and weather, and the resulting demand. The testing set, however, is kept hidden. It acts like a final exam. Once the model has finished studying, we show it the testing data to see if it can accurately guess the demand on days it has never seen before. By maintaining this separation, we can be confident that our model will perform reliably when we eventually use it to run our real-world factory production. With our data ready, we can now train our predictive model. We will start with a classic approach called linear regression. This method is excellent for understanding how different factors directly increase or decrease our demand. In our Python environment, we use a popular library called scikit-learn. We create a linear regression object and tell it to fit the training data. During this process, the algorithm calculates the importance or the weight of each feature. For example, it might find that a high advertising spend consistently correlates with a specific rise in sales for product A. Once this training is complete, the model has essentially created a mathematical map. This map allows us to input tomorrow's expected weather or marketing budget and receive an immediate, data-driven prediction of how many units our customers will likely want to buy. Now let us look under the hood at the actual math that powers our predictions. To represent the relationship between our features and our demand, we use a linear equation. You can think of this as a simple recipe. The formula starts with a baseline value, often called the intercept or bias. This represents our starting point, the demand we might expect even if all our other factors were at zero. To this baseline, we add our different features, such as advertising spend or seasonal shifts. However, not every feature has the same impact. This is why we assign a weight or a coefficient to each one. If a feature like ad spend has a high weight, it means a small increase in spending leads to a large jump in sales. If a feature has a weight of 0, it means it has no influence at all. Our machine learning model works by looking at our historical data to find the exact weights that make our predictions as accurate as possible. It is trying to draw a best fit line that minimizes the distance between our calculated guess and the actual sales we saw in the past. This simple linear structure is incredibly powerful because it is clear, easy to explain to stakeholders, and provides a solid foundation for the optimization steps that follow. Now that we understand the math, let us look at how we translate that theory into a working Python script. On this slide, you see the implementation using the popular scikit-learn library. We begin by preparing our data. We define our features, the independent variables like marketing spend and seasonality, and our target, which is the actual demand we want to predict. Notice that we create two separate models, one for product A and another for product B. This is because, as we discussed, each product reacts differently to market forces. Next, we initialize our linear regression objects. The most important step happens when we call the fit function. This is the moment the machine actually learns. It scans our historical data and calculates the optimal weights for each feature. This code turns our abstract mathematical formula into a concrete tool. We can now feed in future marketing plans and get an immediate, data-driven estimate of our upcoming production needs. Finally, we look at the results. By accessing the intercept and coefficient attributes of our model, we can see the exact numerical values the computer has assigned to our business drivers. Now, let us look at the results in action. This visualization demonstrates how effectively our model captures the demand values driven by external or exogenous variables. If you look at the plots, the green line represents the actual demand, while the red dashed line represents our model's predictions. At first glance, the model seems to follow the general trend. It captures the peaks and valleys to some extent. However, look closer at the gaps between the green circles and red squares. In many instances, especially in demand B, the model overshoots or undershoots significantly. This happens because linear regression struggles with nonlinearities and complex interactions. For example, a promotion might have a massive impact during a holiday, but a negligible one on a random Tuesday. While it gives us a number, roughly 32 for product A and 20 for product B, we need to ask ourselves, can we do better? Can we reduce that error margin? This is exactly why we move toward more sophisticated ensemble methods like XGBoost. A simple linear model often fails to bend enough to capture those nuances. Finally, notice the blue X at the end of the timeline. This is our prediction for the next period. Now let's go under the hood of one of the most powerful tools in a data scientist's arsenal, XGBoost, or extreme gradient boosting. Unlike a single linear equation, XGBoost is an ensemble of regression trees. Think of it as a wisdom of the crowd approach, but with a twist. The trees are built sequentially. As you see in the diagram, we start with tree 1. It makes an initial prediction, but it won't be perfect. It leaves behind a residual, which is just a fancy word for the error. Instead of starting from scratch, tree 2 is specifically trained to predict those errors from the first tree. This is the core of the boosting math shown on the right. Essentially, your prediction at step $k is the sum of all previous predictions plus a new adjustment. This iterative process allows the model to learn from its mistakes. Each new node split in the tree is determined by an objective function that balances predictive power with model simplicity to prevent overfitting. By the time we reach the K-tree, we have a highly refined model where the final prediction is the sum of all tree outputs. This allows us to capture incredibly complex nonlinear patterns that a simple straight line would completely miss. Let's look at how we actually implement this using Python. The beauty of modern libraries is that we can build this complex ensemble in just a few lines of code. First, we define our features. These are the exogenous variables we mentioned earlier: the season, whether a promotion is active, the day of the week, our advertising spend, and even what our competitors are doing. These are the signals the model uses to learn the demand patterns. Once the model is trained, we want to predict tomorrow. We feed it a new recorder-specific scenario where it's a Wednesday. We have a promotion running, and we've spent 30 units on ads. We use a simple for loop to train a separate regressor for product A and product B. The fit method is where the magic happens. That's where those sequential trees we just discussed are actually being built. By calling the predict function, the model traverses all its internal trees and spits out a concrete number. In this case, our XGBoost model predicts a demand of 19 units for product A and 10 units for product B. This snippet represents the bridge between raw data and actionable business intelligence. Finally, let's look at the results. Compare these plots to the linear regression slides we started with. The first thing you'll notice is how the red dashed line, our prediction, almost perfectly overlays the green line, the actual data. This is the power of XGBoost. It has effectively captured the demand values driven by those exogenous variables. It doesn't just follow the trend, it hugs the data points. It understands that the relationship between ad spend and demand might change based on the day of the week. Look at the new point prediction, the blue X at the end of the chart. Because our training error was so much lower than the LR model, we can have much higher confidence in this forecast. For product A, we are looking at a predicted demand of roughly 19. In a real world, this is the aha moment. By moving from a linear model to a gradient-boosted tree ensemble, we've moved from a general guess to a precision forecast. This allows businesses to optimize their inventory, reduce waste, and ensure they meet customer needs exactly when they arise. Now that we've seen how the model predicts, let's look at how we can use these predictions for optimization. Now that we have processed our forecasts through two different lenses, linear regression and XGBoost, it is time to synthesize these results for business decision-making. On this slide, we compare the final outputs for our specific new record scenario. For product A, Our linear regression model forecasted a demand of 32 units, while XGBoost provided a much lower estimate of 19 units. Similarly, for product B, the linear regression model predicted 19 units, whereas XGBoost forecasted only 10 units. It is interesting to note that despite the numerical differences, both models agree on the fundamental trend. Product A is expected to sell more units than product B in this upcoming period. However, the discrepancy between the models presents a classic data science dilemma. Which number do we trust for our inventory and supply chain planning? If we look back at our performance charts, we saw that the XGBoost model was significantly more effective at capturing the actual demand values and historical peaks. Because of this higher accuracy and to mitigate the risk of overstocking, we will adopt the more conservative estimate provided by XGBoost. We will proceed under the assumption that sales will amount to 19 units for product A and 10 units for product B. By choosing the conservative path supported by our most robust model, we protect the business from the costs of excess inventory while still following the clear demand signal that product A is our primary driver. This choice serves as the foundation for the optimization steps we will discuss next. We have arrived at the most critical phase, turning our mathematical forecasts into a concrete production plan for the new record. At this stage, we face a common operational challenger. Warning scenario where our forecasted demand units are lower than our supply capacity. Specifically, for product A, we have a forecasted demand of 19 units against a supply capacity of 32. For product B, the demand is only 10 units, while our supply could reach 36. In a naive system, you might be tempted to produce at full capacity to maximize utilization. However, producing more than the market demands leads to wasted capital and storage costs. Therefore, we need to integrate these demand forecasts into our optimization strategy. To do this effectively, we set an upper bound threshold on supply units. We essentially cap our production at the demand level to avoid oversupply by aligning our production exactly with our conservative forecasts. 19 units for product A and 10 units for product B. We arrive at our new production plan. This precision doesn't just save resources, it maximizes our bottom line. As you can see on the right, this optimized plan leads us to a calculated profit of €10.44.45. This is the essence of data-driven optimization, using machine learning to set the boundaries for our operational decisions, ensuring every unit produced has a buyer weighting and every euro spent contributes to profit. Now, we reach the integration phase where our XGBoost forecasts become formal constraints within our optimization model. In the Python code snippet at the top, you can see how we systematically add constraints for each product in our portfolio. We use a simple for loop to iterate through our products, calling the model add constraint function. The logic here is critical. We specify that X of product P, our production quantity, must be less than or equal to our predicted demand of product P. This is the upper bound threshold. We discussed ensuring we never produce a single unit that the model hasn't justified through data. Once these boundaries are set, we call model optimize function. As you can see from the solver output in the red box, the engine finds the solution almost instantly in just 0.04 seconds in 2 iterations. The results are precise. For product A, where the raw XGBoost prediction was 18.85 units, the optimizer rounds this to an optimal production of 19 units. For product B, with a prediction of 9.68 units, it sets the production at 10 units. The final result is an optimal objective value of 1044.45. This represents our maximum possible profit while staying strictly within the demand limits we predicted. By integrating forecasts this way, we transform a simple prediction into a mathematically sound, profit-maximizing execution plan. Predictive modeling isn't just about the algorithm you choose. It's about the quality of the data you feed it. As we've seen with our demand forecasts, we used variables like season and promotions. But are all those variables equally useful? This is where feature selection comes into play. Feature selection is the process of narrowing down our data to only the most impactful inputs. There are several critical reasons why we do this. Performance and accuracy. By removing noise or irrelevant features, we actually increase the performance of our models. Too much data can confuse a model, leading it to find patterns where none exist. Efficiency. Reducing the number of variables makes training faster and the resulting models easier to build. In a production environment, speed is money. Interpretability. A model with 5 clear features is much easier to understand and easier to debug than one with 50. If a prediction looks wrong, you can quickly trace which feature caused the spike. The fundamental question we must answer is, what are the most important features to demand prediction? Is it the advertising spend? Is it a competitor's price drop? In our next section, we will use Random Forest's internal feature importance metrics to rank our variables, ensuring that our optimization engine is built on the strongest possible foundation. While we've seen the power of XGBoost, it's essential to understand the random forest regressor, another ensemble method that is world-class for determining feature importance. While XGBoost builds trees sequentially, a random forest builds multiple regression trees in parallel. Each tree is trained on a random subset of the data, and their individual results are combined through majority voting or averaging to produce a stable, final prediction. But the real magic for our current goal lies in how this model quantifies importance. As you can see in the formula, we calculate the importance of a feature J by looking at how much it reduces the prediction error. Specifically, the mean squared error MSE, every time it is used to split a node across all T trees in the forest. Simply put, a feature J is important if it often helps reduce prediction error when used in tree splits. This is a game changer for our demand prediction. Instead of guessing if promotion or ad spend matters more, the random forest mathematically tracks which variable consistently cleans up the most error. By leveraging this reduction in impurity, we can rank our features with high confidence. This ensures that when we move back to our optimization model, we are only feeding it the highest quality signals, further refining that €1,044.45 profit margin we achieved earlier. To understand why a random forest is more robust than a single decision tree, we have to look at bootstrapping, the secret sauce that creates diversity within the forest. Imagine you have a single dataset, as shown in the top box. If we trained every tree on this exact same data, they would all look identical and make the same mistakes. To prevent this, we use random sampling with replacement. Each of these unique subsets is then used to train its own individual decision tree because the training sets are slightly different. The trees see the world from different perspectives. Finally, for a regression task like our demand prediction, we aggregate the results by taking the mean of the predictions from all these trees. In the diagram, you can see how we create multiple bootstrap samples. Each sample is the same size as the original, but because we sample with replacement, some data points might appear twice, while others known as out-of-bag samples are left out entirely. This formula is the mathematical representation of wisdom of the crowd. By averaging the output of many diverse trees, we drastically reduce the variance and the risk of overfitting. One tree might be tricked by a noisy data point, but when averaged with 100 others, that noise gets canceled out, leaving us with a stable, reliable forecast for our optimization engine. Each tree T in our forest operates by taking its bootstrap sample, D or T, and splitting the input space into distinct regions at every node. The algorithm's goal is to find the perfect feature, J start, and the perfect split value S star that minimize the mean squared error. Mathematically, we are looking for the split that minimizes the sum of square deviations in the resulting branch's minimization of J and S. Here, R1 and R2 represent the two new regions created by the split, essentially asking, does this feature value fall above or below our threshold S? We calculate the average target value, Y hat, for each region and repeat this process recursively. This continues until we hit a stop criterion, such as a maximum tree depth, to prevent the tree from becoming overly complex. Finally, how do we get a prediction from a single tree? When a new data point falls into a final leaf node or region R, the prediction f of x is simply the mean of all the target values y of I that landed in that specific region during training. By mastering the splitting logic, the tree learns to group similar demand scenarios together, providing the granular insights that the random forest will eventually average out for our final forecast. We have reached the mathematical core of feature importance. In the context of our production planning, we need to know whether promotions or competitor activity is the true driver of demand. To calculate this, we look at every single tree in our forest and attribute the MSE reduction, the decrease in mean squared error, to the specific splitting feature J that caused it. The formula on this slide represents a global average of these improvements. Delta of MSE is the specific decrease in error achieved at a single split S. Splits of J refers to all the times feature J was chosen as the splitting variable within a specific tree T. We sum these reductions across all trees in the forest and then normalize the results so that the importance of all features sums to 1. The fundamental takeaway is highlighted in the blue box. A feature J is considered important if it often helps reduce prediction error when used in tree splits. This isn't just a subjective guess. It is a rigorous accounting of which variables provided the most information gained throughout the entire training process. By identifying these heavy hitters, we can prune away irrelevant data, making our model more robust and our ultimate optimization more profitable. In the next slide, we will see the visual results of this calculation applied to our demand data set. Now we see the results of our mathematical labor. By feeding our historical sales data into the random forest model A, we can finally rank our features based on their true relevance to the target demand variable. This is where we separate the signals from the noise. Take a look at the horizontal bar chart on the right. We have applied a significance threshold of 0.05, represented by the red dashed line. Any feature falling to the left of this line is essentially a distraction for the model. As you can see, season, products promotion, and day of the week have been crossed out. While these might seem important intuitively for this specific dataset, they didn't provide enough predictive power to meet our threshold. The clear winner, labeled with a large red one, is ad spend. It has an important score of over 0.8, meaning it is the overwhelming driver of demand for product A. Coming in at number 2 is competitor activity, which just barely clears our threshold. This visualization is incredibly powerful for a business. It tells us that if we want to change our demand, we should focus our energy and budget on ad spend rather than worrying about the day of the week. By narrowing our focus to these 2 key variables, we can simplify our model, making it more robust and easier to maintain, while ensuring our optimization engine is reacting to the factors that actually move the needle on profit. In this slide, we translate our random forest theory into a functional Python workflow using scikit-learn. The process is divided into 4 clear steps to ensure our optimization model only receives the most impactful data signals. First, we define our features and targets. We list our exogenous variables like season, promotion, and ad spend, and set our target as demand A. Next, we fit the random forest. We initialize the random forest regressor and call the fit method. During this step, the model is busy performing the recursive partitioning and MSE reduction calculations we discussed in the math sections. The third step is the most critical for our goal. We extract feature importances. By accessing the feature importances attribute, we retrieve the normalized scores that represent how much each variable contributed to reducing prediction error. We then apply our 0.05 threshold using a simple list comprehension. This automatically filters our list, keeping only the heavy hitters like ad spend and competitor activity while discarding the noise. Finally, the code visualizes the results. Using matplotlib, we generate the bar chart we saw previously, including that red dashed line representing our threshold. By the end of this script, we aren't just guessing what matters. We have a printed list of selected features that are mathematically proven to be relevant to product A's demand. This lean mean feature set is what we will use to refine our final production optimization. Until now, we have treated the demand for product A and product B as two separate problems. However, in a real-world market, products often behave in similar patterns. This slide introduces a powerful way to visualize that relationship by plotting each historical record as a single point in a two-dimensional demand space. On the x-axis, we have the demand for product A, and on the LA-axis, the demand for product B. Every blue dot you see represents one specific day or record where both demands were measured simultaneously. For example, the point highlighted by the arrow shows a scenario where demand for product A was high around 54 units, and demand for product B was moderate at roughly 23 units. By looking at the clouds of points, we can start to see patterns. Are there days when both products sell well? Or does one product thrive only when the other fails? This spatial visualization is the perfect setup for clustering algorithms. Instead of just analyzing variables, we can group entire historical records together based on how similar their demand values are. This allows us to categorize our business days into high-demand days, low-demand days, or mixed days, providing a new layer of strategic insight that helps us prepare for future production cycles. To turn our cloud of demand points into actionable business categories, we use k-means. This algorithm partitions our dataset into k distinct clusters, where each historical record is assigned to the group with the nearest mean, also known as a centroid. The process is highly iterative and follows 4 logical steps shown in the diagram. We start by randomly placing k starting points that crosses into our data space. In this example, we've chosen k equal to 3. Each data point looks at the available centroids and hitches its wagon to the closest one. This creates our initial orange, blue, and green territories. At means update, this is where the algorithm learns. The centroids move to the actual center point of all the members currently in their group. We repeat the assignment and update steps until the centroids stop moving. At this point, the algorithm has converged and we have mathematically stable groups. In our demand context, this allows us to categorize every day in our history. One cluster might represent high demand for both products while another represents low demand. This clustering is a prerequisite for more advanced optimization. By knowing which state our market is in, we can tailor our production strategies to match the specific characteristics of that cluster, rather than relying on a one-size-fits-all approach. To implement k-means effectively in our demand study, we must understand the mathematical framework that drives the centroid movement we just visualized. We start with a dataset D and a predefined number of clusters, k. The algorithm's objective is to minimize the within-cluster sum of squares, represented by the cost function, j. The process follows a strict mathematical loop. First, we randomly select k centroids within our multidimensional space. Once these starting points are set, we perform the assignment phase. Every data point x of I is mathematically linked to the cluster whose centroid is closest, using the squared Euclidean distance. Next comes the update phase. We recalculate each centroid m at k by taking the mean of all records currently assigned to that cluster. We repeat these steps until convergence, which occurs when the centroids stabilize and no longer change their positions. This means we have successfully found the centers of gravity for different market behaviors, allowing us to categorize days not by date, but by the mathematical similarity of their demand. This transition from raw data points to defined clusters is what allows us to apply specific optimization rules to specific market conditions. We are now applying k-means with 3 clusters to our demand space for products A and B by grouping our 20 historical records. The algorithm has identified 3 clear operating modes for our business, visualized by the blue, orange, and green points and their respective red x centroids. Each cluster carries a unique business implication that should dictate our production strategy. Cluster 0 blue. This represents periods of low sales for both products. When we find ourselves in this cluster, we should consider running new promotions or, more importantly, reducing supply to avoid overproduction and wasted inventory. Cluster 1 orange. These points reflect a steady market. In these periods, our best move is to maintain a stable supply chain while testing different marketing strategies, like adjusting ad spend or specific promos, to see if we can nudge the market toward higher demand. Cluster 2 green. This is our high-performance zone with high sales for both A and B here. The strategy shifts to maximizing production to ensure we don't miss out on revenue, and we might even have the leverage to increase prices. By using clustering, we move away from a one-size-fits-all approach. Instead of treating every day the same, we can now identify which period we are currently in and immediately deploy the optimized business response associated with that specific cluster. This turns raw demand data into a strategic playbook for operations. Implementing k-means in Python requires a few extra steps to ensure the algorithm performs accurately. Our workflow here uses scikit-learn and follows a 3-step process to group our demand records. First, we prepare our data. We extract the demand values for both products and convert them into a 2D NumPy array, creating a spatial representation of every historical record. However, because k-means is a distance-based algorithm, it is highly sensitive to the scale of the data. To ensure one product's demand doesn't unfairly dominate the distance calculation, we use the standard scaler. This centers our data around 0 with a standard deviation of 1, creating a level playing field for the algorithm. Next, we fit the k-means model. We specify k equals 3 clusters and use fit_predict on our scaled data. This assigns each record a labels 0, 1, or 2. Crucially, once the clustering is done, we use inverse_transform to bring our cluster centroids back to their original scale. This allows us to interpret the centroids in real units of demand rather than abstract scaled numbers. Finally, we visualize the results. The code loops through each cluster to plot the data points and marks the final centroids with a red X. By the end of this script, we have successfully transformed 20 individual records into 3 distinct business scenarios, each ready for its own optimized production strategy. We have covered a significant amount of ground, moving from raw historical data to sophisticated operational decisions. This slide summarizes the 3 key takeaways that now form your toolkit for avoiding common business pitfalls. First, we learn how to avoid over-underproduction by using demand prediction models specifically. Linear regression and XG boost as direct inputs or constraints into a Garobi optimization model. We ensure that production levels are always mathematically justified. This protects the bottom line from the dual threats of wasted inventory and missed sales opportunities. Second, we realize that not all features matter equally, using the random forest regressor. We performed feature selection to strip away the noise and focus only on the most significant drivers of demand. This doesn't just simplify our models. It improves our prediction accuracy and makes our strategy much easier to debug and understand. Finally, we looked at how to discover demand patterns for new strategies. By optionally using clustering, specifically the k-means algorithm, we can group periods with similar demand behavior. This allows us to move beyond reactive planning and instead adapt our decisions proactively based on whether the market is in a low sales, steady, or high-performance state. By mastering these 3 steps, you are no longer just guessing at demand. You are engineering a responsive, profit-maximizing supply chain powered by machine learning. Now it's time to put these tools to work in a real-world sandbox. We are moving into a hands-on lab focused on one of the most volatile and interesting sectors for an ML expert, the energy market. To do this, we follow a 3-step workflow that mirrors how data scientists work in the utility industry today. Simulation. We begin with pandas and NumPy. Because real-world high-resolution energy data can be proprietary or messy, we start by simulating hourly electricity consumption. We'll generate features like time of day, day of the week, and temperature to give our model the context it needs to understand why demand fluctuates. Prediction. Once we have our data, we move to the ML phase using auto-regression. Here, we aren't just looking at the past. We are training a model to predict future hourly demand. This is critical because you cannot optimize what you cannot forecast. Optimization. Finally, the brain of the operation, Gorobi. We take those predicted demand values and feed them into a mathematical solver. The outcome is a cost-effective generator dispatch schedule, specifically looking at how to balance the load efficiently at hour 150, a peak period. This ensures we provide enough power without over-generating and wasting money. To build a successful optimization model, you must first understand the nature of the load you are serving. Not all customers pull power from the grid in the same way. If you treat a factory like a suburban home, your optimization will fail. On this slide, we see the three primary load profiles that electric utilities manage: residential, commercial, and industrial. Residential. Notice the distinct camel hump. Demand is low during the day when people are at work, but it spikes sharply in the evening. As people return home, turn on lights, cook dinner, and run HVAC systems, the load surges. This is the most volatile profile to manage. Commercial. This profile follows the standard business day. You see a sharp rise around 8 o'clock or 9 a.m. as offices and retail spaces open, staying relatively high until it tapers off in the evening. The peak happens during work hours. Industrial. This is the baseload hero. Large-scale manufacturing often runs 24/7s or in long, consistent shifts. Consequently, the load remains relatively steady throughout the day. Why does this matter for our Gorobi optimization? Because each curve represents a different challenge. In our hands-on exercise, we are focusing on the residential profile. This means our optimization model must be robust enough to handle that steep evening ramp-up without compromising grid stability or breaking the bank. We are working with a dataset representing 7 full days of activity, which gives us 168 individual hourly records. Our dataset contains 4 critical columns, also known as features that drive our predictions. Temperature. Since heating and cooling are the biggest drivers of residential load, this is a vital predictor. Hour. This captures the daily cycles we discussed, specifically that residential evening peak. Day of week. This helps the model distinguish between a Tuesday morning and a Sunday afternoon. Demand. This is our target variable, the actual amount of energy consumed. Once we know how much energy is needed, the optimization task is to decide where that energy comes from. We have 3 types of power plants available in our portfolio, each with its own cost and capacity profile. Solar power. This is our most sustainable and cheapest option at only €5 per megawatt hour, though it has a limited capacity of 15 megawatt. In an optimization model, we always want to maximize this source first. Coal power. This serves as our mid-range option. It provides a significant capacity of 40 megawatt at a moderate cost of €20 per megawatt hour. Gas power. This is our most expensive peaker plant. At €50 per megawatt hour, it's costly to run. But with a 25 megawatt capacity, it's there to ensure we can meet demand when the cheaper sources hit their limits. Our objective in Gorobi will be to balance these 3 plants to satisfy the residential demand at the lowest possible cost. Now let's look at the actual data we've generated. This visualization illustrates the 168 hours of synthetic multivariate data that our model will process. By plotting these variables together, we can see the relationships that our machine learning model will eventually exploit for predictions. The top graph shows our demand, MWH. I've highlighted the daily peaks with red circles. Notice how consistent these are. Every single day, we see a sharp rise in electricity usage. These peaks represent that residential evening surge we discussed, where demand frequently climbs toward the 70 MWH mark. Between these peaks, the load drops back down to a base load level of around 50 megawatt hours during the late night and early morning hours. The middle graph displays the temperature C over the same 7-day period. You can see a clear rhythmic oscillation, with temperatures swinging between roughly 14 degrees Celsius and 26 degrees Celsius. Notice how the peaks in temperature often precede or coincide with the peaks in demand. In our model, this correlation is a vital feature for the regression algorithm. Finally, the bottom graph shows the day of week. It's a simple step function, moving from 0 Monday to 6 Sunday. This tells the model exactly where we are in the weekly calendar. While the daily peaks look similar, look closely at the weekend Saturday and Sunday. The shape of the demand curve often shifts slightly compared to a Monday or Tuesday. Understanding these subtle variations is what separates a basic forecast from a high-performing energy model. Now that we understand our variables, let's look at how we actually construct this environment in Python using pandas and NumPy. We start by setting a random seed to ensure that our results are reproducible, meaning you'll see the exact same numbers on your screen as I have here. Our first step is to initialize a data frame with 168 records representing one full week. We use np.tile to repeat the 24-hour cycle 7 times for the hour column, and np.repeat to ensure each of the 7 days is assigned to 24 consecutive hours. Next, we simulate the temperature cycle. We use a sine wave function to model the natural rise and fall of temperature throughout the day, centered around 20 Celsius with a 5-degree fluctuation. To make it realistic, we add a bit of Gaussian noise using NP random normal, ensuring our data isn't a perfectly smooth artificial curve. The most critical part of the simulation is how we define our demand megawatt hour. We don't just pick random numbers. We build a logic-based model that reflects real-world residential behavior. The baseline: we start with a standard base load of 50 megawatt hour. The evening peak: we use a conditional statement to add 10 megawatt hours specifically between the hours of 18 o'clock and 21 o'clock. This mathematically creates those red-circled peaks we saw in the previous visualization. The temperature effect: we incorporate a heating logic where cooler temperatures increase the demand. Specifically, for every degree, the temperature drops below 30 Celsius. The demand increases by 0.5 megawatt hour. Random noise: finally, we add a final layer of random noise to simulate the unpredictable nature of human energy consumption. The result, as you can see in the table on the right, is a clean 4-column dataset ready for our machine learning model. We have successfully moved from a conceptual demand pattern to a concrete, programmable data structure. Now that we have our core dataset, we move to feature engineering and data partitioning. In machine learning, raw data is rarely enough. We often need to help the model by creating features that highlight specific behavioral patterns. We begin by defining our initial feature set, X, which includes our primary drivers, the hour of the day, the temperature, and the day of the week. However, based on our previous observation of residential load, we know that the period between 18 and 21 is unique. To capture this, we create a peak hour flag. This is a binary variable, a 1 or a 0, that explicitly tells the model whether a specific record falls within that critical evening surge. We take this a step further by creating an interaction variable, temp_peak_interaction. By multiplying temperature by our peak hour flag, we allow the model to learn if the impact of temperature changes specifically during those high-demand evening hours. This kind of domain-specific feature engineering is what transforms a generic regression into a powerful predictive tool for energy. Once our features are engineered, we define our dependent variable, y, which is the electricity demand we want to predict. But before we can train a model, we must address a fundamental rule of machine learning: never test a model on the same data it used to learn. We use the train_test_split function to partition our data, allocating 80% for training and 20% for testing. You will notice a very important parameter here: shuffle equals false. In standard machine learning, we often shuffle data to ensure a random distribution. However, because energy demand is a time series, the order of the data matters immensely. By setting shuffle to false, we ensure that the model trains on the past the first several days and is tested on the future the final portion of the week. This approach provides a realistic simulation of how the model would perform in a real-world utility setting, where it must predict tomorrow's load based on everything it learned up until today. As we advance our predictive capabilities, we must address the temporal nature of energy data using specialized statistical models like ARIMA and its seasonal extension, SARIMA. While standard regression treats each hour as an independent data point, ARIMA recognizes that electricity demand is a univariate time series, meaning the value at any given hour is often a function of its own past. The acronym ARIMA stands for three distinct components that work together to model complex data. A are autoregressive, represented by the parameter p. This accounts for the effect of past values on the current value. It assumes that if demand was high an hour ago, it is likely to remain relatively high now. I integrated, represented by d. This involves differencing the data, subtracting the previous value from the current one to achieve stationarity. This removes trends so the model can focus on the underlying patterns. Moving average, represented by q. This captures the effect of past prediction errors. It helps the model adjust based on how far off its previous guesses were. While a standard ARIMA model is powerful, it often falls short in energy markets because it doesn't natively account for cycles, like the 24-hour residential peak we've been studying. This is where SARIMA comes in. By adding a seasonal component denoted in parentheses as PDQS, the model can specifically capture recurring patterns at fixed intervals, such as a seasonal period S of 24 hours. In the notation shown on the slide, the lowercase pdq represents the non-seasonal part of the model inherited from ARIM. The uppercase PDQS represents the seasonal components that look back at the same hour from previous days. By combining these, we create a robust forecasting tool that understands both the immediate momentum of the grid and its long-term rhythmic behavior. This methodology remains a cornerstone of time series analysis and provides the mathematical rigor needed to feed accurate demand forecasts into our Gurobi optimizer. In this slide, we bridge the gap between theoretical time series analysis and practical application through autoregression. As the title suggests, we are modeling our target variable, demand at t, as a direct function of its own history, specifically its previous value, demand t-1. This approach is fundamentally built on the concept of autocorrelation, which is the tendency for current electricity demand to be highly correlated with what happened in the immediate past. Our workflow for this task follows a clear three-stage pipeline. The input is the lagged demand data. We then apply our method, partitioning our simulated data sets into an 80% training set and a 20% testing set to validate our results. Within this framework, we train a SARIMA model, which, as we previously discussed, is designed to capture both the immediate momentum of the load and its 24-hour seasonal cycles. The final output of this process is our predicted demand T. Why do we expect this specific method to perform so well? It's because energy consumption isn't random noise. It follows a predictable physical and behavioral momentum. If the neighborhood is using 60 megawatt hours at 6 p.m., it is statistically very likely to use a similar amount at 6:05 p.m. or 7 p.m. By leveraging these autoregressive properties, we can generate a high-fidelity forecast that serves as the fuel for our optimization engine. Without this predictive step, our Gurobi solver wouldn't know how much power to dispatch. This slide marks the transition from understanding our data to actually making it actionable for the utility grid. We translate the theoretical principles of time series analysis into executable Python code using the StatsModels library. Our objective here is to fit a SARIMA model specifically designed to handle the hourly seasonality of our residential demand data. The model configuration is precise. The non-seasonal order 1, 0, 1. This tells the model to look at the immediate previous hour to establish a baseline for the current prediction. The seasonal order 1, 1, 1, 24. The crucial parameter here is 24, which instructs the model that our season is a full day. This allows the algorithm to understand that demand at 7 p.m. today is likely very similar to demand at 7 p.m. yesterday. We also disable strict stationarity and invertibility checks. Enforce stationarity equals false to ensure the model fits successfully, even with our noisy synthetic dataset. Once the model is defined, we execute model fit to train it on our 80% training set. With the model trained, we move to the final predictive phase, forecasting the last 20% of our week. This represents the unseen future, where we test the model's true accuracy. By using res forecasts, we generate a full sequence of predicted values that match the length of our testing period. Finally, we store these results back into our main data frame under a new column called Predicted Demand SREMA. This column is the ultimate output of our machine learning pipeline. We have successfully moved from raw historical data to a data-driven prediction of future electricity needs. These specific numbers will now serve as the target demand for our Gurobi optimization, determining exactly how much power our coal, gas, and solar plants need to produce. We have now reached the visual validation of our machine learning pipeline. This chart displays the performance of our SREMA forecast by plotting the actual demand against our model's predictions over the full 168-hour period. The blue line represents the ground truth, the actual demand, values we simulated earlier, while the dashed vertical line marks our test split. Everything to the left of that line was used to train the model, and everything to the right is the future data the model had to predict. As you can see, the SREMA model, represented by the orange line, does an exceptional job of capturing the hourly trends and daily cycles. It successfully mirrors the rhythmic peaks and valleys of our residential load, proving that the S equals 24 seasonal parameter we set is correctly identifying the 24-hour patterns in human behavior. However, a perfect model doesn't exist in the real world, and our visualization highlights that reality. While the orange forecast line follows the general shape of the blue actual demand, you will notice small deviations. These occur because, while SREMA is excellent at capturing recurring cycles, it can struggle when unexpected variations or random noise dominate the signal. Despite these minor discrepancies, the forecast is highly accurate for our purposes. We now have a reliable, data-driven prediction of electricity demand for the final 20% of our week. This is a critical milestone. We are officially moving out of the predictive phase of our project and into the prescriptive phase. We will take these orange predicted values and feed them directly into our Gurobi optimizer to determine the most cost-effective way to dispatch our coal, gas, and solar plants. But before, we can also approach forecasting through a multivariate regression lens. In this model, we treat electricity demand as a function of external factors, rather than just a sequence of time. This allows us to account for the physical drivers of energy consumption. Our input features for this specific model include current hour, the time of day; current temperature, the current outdoor temperature; current day of week, the specific day, identifying weekly patterns; and finally, current temp * peak hour, that crucial interaction variable we created to capture how temperature impacts demand differently during high-activity evening hours. The method follows a similar rigorous path to our earlier forecasting tasks. We maintain an 80% training and 20% testing split to validate the model's predictive power. However, unlike the SREMA model, which forecasts forward into the test set, here we train the model and then use it to predict demand across all 168 hours of our dataset to evaluate how well it fits the overall trend. The final output is once again our predicted demand at time t. By using a regression-based approach, we gain a different type of insight. While SREMA captures momentum, this regression model captures causality. It tells us why the demand is changing based on the weather and the clock. This provides a secondary, robust forecast that we can compare against our SREMA results before finalizing the inputs for our Gurobi optimization dispatch. On the left, we implement XGBoost, a high-performance gradient boosting framework. We initialize the XG beergresser with a default setting and a random state of 42 to ensure your results match mine exactly. XBoost is particularly effective here because it can capture nonlinear relationships. such as how demand might spike exponentially rather than linearly as temperatures drop. We train the model on our X-train and white range sets and then generate a full 168-hour forecast stored as predicted demand X-boost. On the right, we implement a more traditional linear regression model using scikit-learn. This serves as an excellent baseline for our forecasting task. Linear regression assumes a straight-line relationship between our predictors and the load. While simpler than X-boost, it is highly interpretable and often surprisingly effective when we have engineered strong features like our interaction variables. Following the same pipeline, we fit the model to our training data and use the predict method to generate a demand forecast for the entire week. By the end of this task, your dataset will contain 3 distinct forecasts, one from SREMA, one from XGBoost, and one from linear regression. This ensemble of predictions gives us a robust set of inputs to choose from before we move into the final, critical stage of our project, the Gurobi Cost Optimization Dispatch. We have now reached the moment of truth for our predictive analytics pipeline. This slide presents a comparative visualization of all our forecasting models against the actual demand for the test period, starting from the train boundary at our 134. By plotting the actual demand blue line alongside our 3 candidates, SREMA, orange, XGBoost, red, and linear regression, gray, we can visually audit which algorithm handles the complexities of the energy grid most effectively. As we examine the fluctuations, you will notice that while all models generally follow the correct upward and downward trajectories, their precision varies significantly at the peaks. For instance, around hour 140 and hour 163, we see sharp spikes in consumption. Some models overrespond to these peaks, while others underestimate them. This visual competition is essential for a data scientist because it reveals the personality of each model, how they handle noise versus how they handle signal. The key takeaway from this comparison is clearly highlighted at the bottom of the slide. SREMA consistently aligns more closely with the actual demand across the test period. Despite the sophistication of machine learning models like XGBoost, the seasonal statistical approach of SREMA proved superior for this specific residential load profile. Its ability to lock onto the 24-hour cycle allowed it to track the blue actual line with the least amount of deviation. Now, why does this accuracy matter so much? Look at the black arrow pointing to hour 150. This represents our designated point for the optimized dispatch plan. If our forecast is off by even a few megawatt hours, our optimization could either fail to meet demand, causing a blackout, or over-allocate expensive gas plants, wasting money. Because SREMA provides our most reliable prediction, we will use its output for our 150 as the target demand for our final task, using Gurobi to create the most cost-effective generation schedule. We have reached the prescriptive climax of our module, the dispatch optimization plan. Now that we have a reliable demand forecast for hour 150, we use Gurobi optimization to determine exactly how much power each of our plants should produce. The goal is to minimize the total operational cost while strictly adhering to the physical and systemic limits of our energy grid. To translate this business problem into a mathematical model, we define 3 core components: decision variables, constraints, and the objective function. Our decision variables, denoted as X of P, represents the specific amount of power in megawatts dispatched from each plant P in our portfolio. These are the knobs the optimizer will turn to find the best possible solution. As we defined in our data description, P represents our coal, gas, and solar facilities. Every optimization model must live within the boundaries of reality, which we define through constraints. Predicted demand balance. The sum of power from all plants must exactly equal our predicted demand D. This is expressed mathematically as sum of generation equal to demand. This ensures the lights stay on at our 150 based on our SREMA forecast. Max capacity limits. Each plant has a physical ceiling. the power dispatched from a plant must be greater than or equal to 0 and less than or equal to its maximum capacity, P. This ensures we don't ask our 15 megawatt solar plant to produce 20 megawatt. Finally, we have the objective function. In the energy sector, we aim for economic dispatch, which means we want to minimize the total cost of the power plant's P. We calculate this by multiplying the cost of each plant C of P by the power it produces X of P, expressed as minimization function. Gurobi will process these equations to find the specific values for coal, gas, and solar that satisfy our demand at the absolute lowest price point. We are now at the final stage of our technical journey, the implementation of our economic dispatch model in Python using the Gurobi optimizer. Our objective is to take the demand prediction for our 150, which we identified as our best performing SARIMA forecast, and determine the most cost-effective way to generate that electricity. We begin by defining our generation fleet as a dictionary, incorporating the parameters we discussed earlier. Coal, costing €20 per megawatt hour with a 40 megawatt capacity. Gas, our expensive backup at €50 per megawatt hour with a 25 megawatt capacity. Solar, our priority source, costing only €5 per megawatt APR, though capped at 15 megawatt. Once we've extracted the specific demand value from our data frame at index I equals 150, we initialize the Gurobi model using GP model and create our decision variables, X, representing the dispatch amount for each plant. We set a lower bound of £0 equals 0 because a power plant cannot produce negative energy. With the foundation set, we translate our mathematical logic into code. First, we set the objective function using setObjective. This uses GP-quick sum to calculate the total cost by multiplying each plant's specific cost by its dispatch variable. And we instruct Gurobi to minimize this value. Next, we apply our two critical constraints. Demand balance. We ensure the total output from all plants exactly matches our predicted demand to SARIMA for that hour. Plant capacities. We loop through each plant to ensure the optimizer never dispatches more power than the plant's maximum physical capacity. Finally, we trigger optimize. Gurobi's algorithms will instantly navigate the feasible region to find the optimal dispatch mix, exhausting our cheap solar first, then filling the gap with coal, and only utilizing expensive gas if absolutely necessary. This completes our full pipeline, from raw data simulation to a high-fidelity forecast, and finally, a mathematically optimized decision. We have reached the final result of our end-to-end pipeline. This slide visualizes the optimal dispatch allocation for our 150, where our Gurobi optimizer has translated mathematical constraints into a concrete operational plan. The stacked bar chart on the left shows exactly how the load is being met. The red dashed line at the top represents our predicted demand of 53.29 megawatt, which was provided by our eSARIMA model. To meet this demand at the absolute lowest cost, the optimizer has made the following strategic allocations. Solar Green, dispatched at its maximum capacity of 15.00 megawatt. Because solar has the lowest cost at only €5 per megawatt hour, the model utilizes every available megawatt before looking elsewhere. Coal Light Blue, dispatched at 38.29 megawatt. Since solar wasn't enough to cover the total 53.29 megawatt demand, the optimizer turned to our next cheapest source, coal, which costs €20 per megawatt hour. Gas Orange, dispatched at 0.00 megawatt. Because the combined capacity of solar and coal was sufficient to meet the demand, the optimizer correctly chose to keep our most expensive peaker, plant at €50 per megawatt hour, turned off entirely. The final economic outcome is a total dispatch cost of €840.72 for this specific hour. This result perfectly demonstrates the value of prescriptive analytics in the energy sector. By combining a high-accuracy machine learning forecast with a robust optimization solver, we have ensured grid stability while maximizing profit and sustainability. Note the icons on the right. The flame for gas has a red line through it. reinforcing that in an optimal scenario with this level of demand, we avoid expensive fossil fuels whenever possible. You have now seen the full cycle, from simulating noisy residential data to engineering features, training a SARIMA model, and finally, using that forecast to drive a cost-minimizing dispatch decision in Gurobi. This framework is the gold standard for modern smart grid management. As we conclude this hands-on session, let's synthesize the three critical pillars of our residential energy dispatch project. Our journey has demonstrated how data science and mathematical programming intersect to solve real-world utility challenges. The first pillar is load forecasting. We established that electricity demand is not a series of random events, but a predictable, univariate time series. By leveraging the autoregressive nature of demand, the fact that current usage is deeply linked to past values, we successfully applied the SARIMA model to capture both hourly trends and 24-hour daily cycles. This provided the predictive foundation necessary for intelligent decision-making. The second pillar is the integration of load forecasting into Gurobi optimization. We learned that a forecast is only as valuable as the actions it informs. By taking our forecasted load and using it as a primary constraint in our Gurobi model, we ensured that our total energy dispatch across all power plants was perfectly balanced to meet consumer needs. This ML model plus optimization framework is what allows modern grids to operate efficiently. Finally, we have the optimization plan at a given time. At hour 150, our model didn't just give us a number. It provided an explainable dispatch plan. We saw exactly how the optimizer prioritized our 15 megawatts of cheap solar and 38.29 megawatt of coal to meet a 53.29 megawatt demand, while completely avoiding expensive gas. This resulted in an optimal total dispatch cost of €840.72. You now have a complete end-to-end template for moving from raw synthetic data to an optimized, cost-effective energy strategy. To continue your learning journey, I've also included links to several open-access datasets. Practicing with real-world data from the EIA Energy Information Administration or the Global Energy Forecasting. Competition is the best way to test the limits of the XGBoost and linear regression models we built today. Remember, the goal of this course isn't just to teach you a set of formulas, but to equip you with a powerful analytical mindset. By mastering the connection between a predictive forecast and a prescriptive optimization, you now possess the skills to transform raw data into actionable, cost-saving decisions. Thank you for joining me in this session. I look forward to seeing how you apply these techniques to build the smarter, more efficient energy grids of the future.